We're going to continue on talking about thermochemistry like we were talking about before, thermodynamics. Get a couple of things out of the way here. Okay, so we started talking about thermodynamics in this chapter, and remember when we're talking about sort of thermodynamics, what we're referring to is really sort of the overall idea of kind of what is known as sort of spontaneity, and what we're really looking at in a lot of cases is whether or not a particular reaction will be spontaneous. And what that means is, it doesn't necessarily mean that, the reaction occurs super fast or maybe super slow if it is spontaneous. What it means is if it is spontaneous, under those conditions, we would expect a sort of reaction to occur. And again, that reaction may be really fast, it may be really slow, but we would expect at some point under those conditions, if it is spontaneous, for it to actually sort of occur. When we talk about sort of how fast or slow a reaction occurs, that's more what is referred to as kinetics, which we'll talk about obviously in this class. And that deals with the obviously speed or how fast or slow a reaction occurs. But here, a lot of what we look at is that idea of, again, will it actually just occur under those conditions, regardless of sort of speed or how fast or slow it might actually happen. So there are some thermodynamic sort of properties and values that you probably have seen before. We talked a little bit about it last time, but delta H, which is the enthalpy, is a sort of thermodynamic sort of value that is basically, if it is negative, it is an exothermic reaction. If it is positive, it's a endothermic reaction. And again, endothermic obviously meaning heat and energy is absorbed. Exothermic meaning obviously heat and energy is released. And we have sort of really the first law of thermodynamics, which maybe they don't call it that all the time, but is sort of that law of conservation of energy. And that's where we dealt with a lot of energy and stuff like that. And as we sort of touched upon last time towards the end there, the idea of, if we do have sort of a exothermic reaction, like a negative delta H, does that mean that the reaction will be spontaneous? And sometimes people sort of correlate sort of energy to spontaneity. And as we talked about last time, it doesn't necessarily mean that, the reaction will be spontaneous. It doesn't necessarily mean the reaction will be non-spontaneous. As we saw, I think in a slide, a couple of slides back, there is a number of spontaneous reactions that are both exothermic and endothermic. So, for example, the melting of the ice cube is endothermic, but still a spontaneous sort of process that occurs. So the use of sort of enthalpy or energy in that sense to determine whether or not a reaction is going to be spontaneous is not necessarily sort of your overwhelmingly choice in terms of determining spontaneity in a reaction. As it mentioned, it does help a lot of times if we do have sort of an exothermic reaction. It can definitely help in terms of spontaneity, but it's not really the thing that we can kind of look at. One place where we can sort of look at that or help us kind of move in that direction of understanding whether or not a reaction is going to be spontaneous is another thermodynamic sort of property, which is known as delta S. And delta S is the change in entropy. So that's the change in entropy, not enthalpy. And entropy is a little bit different than enthalpy in the sense that it has to do with the amount of disorder and randomness that is happening. So when we talk about entropy, we're talking about randomness, we're talking about disorder that's happening. And actually, when we get an increase in the entropy, we're making more disorder. So as the disorder sort of increases, so does the entropy value, and it actually becomes more of a positive number in that sense. So when we do something, say in a chemical reaction or something of that nature, and we'll talk about some sort of instances of how you could kind of maybe identify the change in disorder. I guess just the upwards arrow doesn't really describe a lot there. An increase in disorder there. It will increase the entropy, and a little bit different than most thermodynamic things, it actually gets more positive in terms of the value when we sort of increase it. And opposite is true if we sort of decrease the disorder, which like we talked about last time. You can also do this with order and order on both sides. If we decrease the disorder, we're increasing the order, and the delta S becomes more negative in that sense. So very common sort of things that can sort of increase the entropy are changes of state. For example, if we go from something from solid to liquid, liquid to gas, and so forth, we're creating more disorder. There's more molecules and stuff moving around, and we increase the entropy. We also talked about, and we'll see it a little bit in here as well, is, when we deal with sort of thermodynamic type properties, we oftentimes think about things in sort of two ways. One way being something being like the system. The system is usually, what you are interested in, what you're working on. So again, if you're doing sort of a chemical reaction in a test tube or a chemical reaction in a beaker, that would be obviously your system. The surroundings is pretty much everything outside of that is, again, your surroundings in that case. So we started talking about also at the very, very end, we saw sort of an equation, sometimes referred to as the Boltzmann equation there. And it has that entropy is equal to K, which is Boltzmann constant, natural log there of W, which is the number of microstates. So we sort of touched upon the idea that, probability and sort of entropy are sort of related to each other. Again, if there's sort of many different ways you could sort of accomplish something, it's a pretty good chance that you're going to accomplish that, and a good probability that that's going to occur. If there's really only sort of one way to do something, there's going to be a low entropy value because of that, because it's got to be pretty much done correctly and kind of done in an ordered fashion. So if you just think about that sort of natural log of the microstates, or W, if you remember from the previous slide, I think, if you just put the natural log of 1 in your calculator, that obviously equals 0, which means you have a very low entropy value. Obviously, I think maybe there's an example of the circles. There's 6 different ways. And, if you did like the natural log of 6, for example, of 1 point something, so a much higher number, obviously, than 0, and a much increase in sort of the entropy value. Any questions on any of that stuff that we talked about last time? Okay. So I think this is sort of where we left off. So these are all sort of processes that lead to an increase in the entropy value. And again, when we increase the entropy, we're increasing the disorder, decreasing the order. And that means that our change in entropy will become more positive in that effect. So these are some of the things that we touched upon before. Obviously, if we go for solid, right? If you have something that's in the solid state, especially something, for example, that's ionic, they're very well ordered. They even have a very long range, repeatable type patterns. Perhaps you remember things like unit cells. We ever talked about those things, especially with solids. And again, that's basically a part of the solid that's basically very repeatable, and you can basically rebuild the entire structure from that repeatable sort of unit of it. But obviously, we go from solid to liquid. In the solid state, everybody's pretty well ordered, pretty tight to each other, not a lot of room of movement. In the liquid state, obviously, we are still pretty close to each other, but obviously, you can see a little bit more room for movement here. So we're going to get more disorder happening. You can kind of think about it, got a lot more people kind of moving around, right? So it's going to create some more disorder. Obviously, if we continue that process and go from liquid to gas in the gas state, right, these guys are pretty much flying all around. And obviously that is a lot more disorder. So as we saw before, solid has a much lower entropy than liquid, and liquid a much lower one, obviously, than the gas phase, as they are all flying around. Or in my case, I'm just drawing arrows all over the screen here. The process of making a solution as well is also a process that increases the entropy. It actually increases the entropy for both parts of the solution. So if you remember, right, a solution is made up of a solute and a solvent, the solute being something that's being dissolved, and the smaller part in the larger part, which is the solvent. And again, before, you sort of dissolve it together, the solvent, like for example, something like water molecules, they would all be together in hydrogen bonding in a very organized sort of fashion. Same thing with our, say, ionic solid here, very organized. When it comes together, we got to break apart all these bonds. We got to break apart some of these bonds. And now we're making some new bonds, obviously creating a lot more disorder. Everybody's mixed together, and we would expect an increase in the entropy value of that case. Temperature as well, right? So temperature has an effect. When we increase the temperature, we're pretty much, giving more energy to the molecules. And as that temperature increases, they have more energy. More energy means they can kind of move around a lot more. And we would expect, something at a larger temperature to be more sort of increase in entropy, a lot more disorder that's basically happening. Any questions on any of those there? So once you take a second for each of these, decide for the system, each of them, does the entropy increase or does the entropy decrease? So take a minute here and think about each of these and think about, would you expect the entropy to increase or decrease in each of these sort of situations? We're sort of increasing the disorder or decreasing it. So condensating water vapor, condensation basically means that we are going from gas back to liquid. So we're going from a system where we have molecules flying around to a system where they're not flying around so much anymore, obviously in the liquid state. So we would expect the entropy here to decrease. The amount of disorder is going to decrease. And what that means in terms of the value of delta S is we would expect it to be negative in this case. Again, a negative delta S means that we have a lot more order, a lot less disorder. And again, that's sort of what's happening, obviously, as we're going from gas to liquid. Looking at the second one, forming a sucrose crystal from a supersaturated solution. Well, this word right there is kind of the important part there. That is a crystal like a solid. And so we're basically forming something kind of in a solid form. A nice perfect crystal means that we would obviously be decreasing the entropy as well in this case. And again, that delta S would be less than 0 or a negative value in this particular case. Heating hydrogen from 60 to 80 degrees, here we are increasing the temperature. And obviously, as we just talked about, more energy means that we would expect the hydrogen gas molecules to, they're flying around like this, to, start flying around a lot faster. Maybe not that much faster, but obviously, since they are moving around a lot faster, that's going to increase the randomness and increase the disorder. And that's also going to make the entropy increase as well. And we would expect the delta S to be greater than 0 or a positive value in this case. And lastly, sublimation. Sublimation is a process where we go from solid directly to gas. We skip the whole liquid process there. And obviously, we are going from something that's very ordered in terms of solid to something where we got gas molecules basically flying around. And thus, we would also expect here the entropy to increase, and we would expect it to be greater than 0 and also a positive number. Any questions on any of those there? Okay. So let's talk a little bit more about entropy. Now, entropy is a state function, and a reminder about state functions is a state function is basically something that is determined by basically two states, if you will, kind of where it started and where it ended up. How you get there doesn't really matter. So things like energy, enthalpy, pressure, volume, temperature, entropy. These are a lot of things that we do if we're trying to calculate like final minus initial, right? And something like the graph here, which shows about potential energy, is both hikers started at the same location. And the blue hiker took the more direct route up the hill. The red guy took the more scenic route around the hill. But in terms of like their potential energy, they are both essentially at the same location at this point, and they both really started at the same location, and they would have basically the same potential energy. It doesn't matter that the guy in the red path there took the scenic route versus the more direct route there by the blue one. This is sort of very similar to Hess's law. So remember that if you're looking at, say, an overall reaction, you can maybe build that reaction by doing, 3 individual reactions that add up to it, maybe 6 reactions that add up to it. And you might even find a way to go kind of like 1 reaction to get there as well. So state functions are things that really the 2 most important sort of aspects of it is kind of where you started and where you finished. And that's why we do a lot of like final minus initial, or if you think about reactions, a lot of things like delta H, for example, that we calculate is products minus reactants, right? And if you think about a chemical reaction, reactants is like your initial, right? And products is pretty much where you ended up, right? Which is like your final. And that's why in a lot of these sort of thermodynamic calculations, we do the difference between, say, the products and reactants in a chemical equation, because that's sort of like where we started and where we ended up. So kind of initial and final conditions when it's all said and done. This is a table of some entropy values, and obviously the table would be provided for you, the values would be provided for you. But there is a couple of things that, it's important to keep a note of that's a little different in terms of delta S values that you would find in a table versus, say, delta H values. First major difference, and also an important one that we'll see in this chapter, is units. Delta S is typically joules, is the units that we go with. Delta H is typically kilojoules. So that's a major sort of difference as well. Another major difference is, perhaps you might remember, if you look up on a delta H table, things in their standard state, uncombined, they have values of 0. So like O2, H2, N2, these things in their sort of standard states, they have values for delta H of 0. In delta S, you will also find values for those things. So you will find some values for things in their natural standard state. And I think we might even have maybe something on this table, like here's O2, for example. On a delta H table, that would be 0. On this table, you will actually find a value. Another difference in terms of the values is they're pretty much positive values. So delta H's could be positives or negatives, but for the most part, delta S values that you would find on the table are going to be, positive numbers. So those are some important things to keep in mind, those units. Sometimes people always kind of zero things out sometimes when they're doing entropy calculations, because they remember delta H, those things are 0, but that is actually not the case here. So in terms of thermodynamics, which is what we're talking about, and as I sort of mentioned a little bit earlier, the first law of thermodynamics is all that energy stuff that you probably dealt with in the previous class, and that is the first law of thermodynamics, which energy can be converted from one form to another, but we don't create nor destroy it. It's all our delta H's. And if you remember, when you sort of talked about that, sort of the same idea I'm imagining that you learned was the system surrounding sort of situation, that if the system, for example, loses a certain amount of energy, it's just not lost. It's the surroundings that basically pick up the exact same amount of energy. So there's this almost perfect sort of transfer of energy from like the system to the surroundings, or the surroundings to the system, and we don't lose anything along the way. Now, the second law of thermodynamics is sort of what we're talking about here, which is basically the entropy of the universe is increasing in a spontaneous process and remains unchanged in an equilibrium process. So the way that we use entropy to determine if a reaction is going to be spontaneous or not is we actually need to calculate 2 different things to help us figure that out. We need to calculate one thing, but in order to calculate that one thing, we actually need to figure out 2 individual calculations to help us decide. And that is right here. You need to usually calculate the delta S of the universe. And the delta S of the universe is the delta S of the system, which is, like your reaction that you're doing, and the delta S of the surroundings. And if you calculate the delta S of the system and also the delta S of the surroundings, which we'll talk about how to do that in just a second, and you add them together and you get a positive number, that basically means that the reaction is going to be spontaneous. Now, if you add them together and get a negative number, that means the reaction would be non-spontaneous in that particular case. If you happen to add them together and they equal 0, that means that you're at an equilibrium process. And, pretty much it's reached equilibrium. So there's no real change sort of happening at that particular point. So let us talk about how to sort of calculate each of those, both the delta S of the system, which is also sometimes referred to as like the delta S of the reaction, because again, as we talked about, in most cases, the reaction is sort of the system that you're looking at in most cases, and how to calculate the delta S of surrounding. We're going to start with the system. So to calculate the delta S of the system or the reaction, we basically do it very much like what we do with delta H. So if you're given a reaction and that's all you're given and you're asked to calculate the delta S of the reaction, by the way, the little knot there means sort of initial conditions, standard conditions. And when we talk about standard conditions, those are usually like table conditions, like 25 degrees Celsius if we're talking about the temperature. The pressure is 1 atmosphere if we're dealing with pressures. The molarity is 1 molar if we're dealing with concentration. So that little knot is usually sort of under standard conditions is sort of what that refers to. And if you're given a problem just like this, where you just have the equation and they want you to find something like this, you pretty much go to a table. That's a pretty good indication that you should go to the table and you should go to the delta S table. And you basically should look up the values for everybody. And when you do, you basically will take the delta S of the products minus the delta S of the reactants. So again, our sort of final state minus initial state sort of situation going on here. A couple of things, just like you would do with delta H, you do take the coefficients into account. So if you had like 2A plus 3B, you would go to the table and take 2 times the delta S for A plus 3 times the delta S for B in that particular case. And that's what you want to make sure that you do. Also very important, obviously, when you go to that table is you want to make sure that you find what you are looking for, but just as important is actually finding the correct state. So remember, when you go to these tables, and you might remember from using like a delta H table, that you not only want to find what you're looking for, but you want to make sure it's in the correct state. Is it solid, liquid, gas, aqueous, whatever it may be? You want to make sure that you look it up in that correct state. Otherwise, you'll get the wrong answer. So water is a very common one like that. You can have water and obviously the gas, liquid, or solid state, and you will find different values for those guys. So you want to make sure that you do look them up in the correct state. So products minus reactants, multiplying the values from the table by the coefficients. You add up all the total entropy value for your products. You then subtract it from all the total entropy value from your reactants, and that should give you an answer. Any questions on that there? All right, so why don't you try one here? These are the values that you would find from the table there. So why don't you calculate the delta S for this reaction and see what you come up with. So take a moment or two and we'll talk about it. Okay, let's take a look here. So again, if this was all you were given, temperature just kind of tells you, this like table sort of values, so you're good. If it doesn't give you a temperature, you probably are safe to assume it's like table value type things. So we would go to the table like this. And again, that's where all these values would come from. To calculate our delta S for this particular reaction here, we would do our products minus our reactants. So we'll start on the product side. That is 2 CO2s. So we would take 2 times the value from the table of CO2 there. That takes care of all the products. We would then subtract it from our reactant side, and we have 2 COs. So 2 times the value of CO, 197.9. And we would then add it to our other reactant, which is O2. And as again, you can see, unlike delta H, there is a value for O2. And in this case, it is 205 joules. So if we do all that, 2 times 213.6 minus 2 times 197.9 plus 205, it looks like, gives us minus 173.6. And again, the units here would be joules. And that would be our entropy value here. The units would be all those things, joules per Kelvin per mole, but I'll just write joules for now. And it is negative. So what does this mean, this value? Does this value mean that the delta S of this reaction is negative? Does this mean that, I'm going to spit this out, right? Does this mean that this reaction is non-spontaneous because of that? And the answer is don't know. So you cannot make that determination at this point by just simply calculating the delta S of the reaction. Remember, you have to calculate the actual delta S of the universe. So you cannot make that determination really at this point if this actual reaction is going to be spontaneous because of positive or negative. Any questions on that? Now, can we sort of predict if our number is sort of right? And the answer is yes. You could actually kind of look at the reaction, and actually before you even do the calculation, you could kind of make a prediction as to whether or not you would expect this guy to be a positive or negative value. So you might be asking, how do you do that? Well, we look on the reactant side here, and we see 2 gas molecules there and 1 more gas molecule there. So we're actually starting with 3 gas molecules here. When we're done with the reaction here, in our final sort of state, we have only 2 gas molecules. So what does that mean? Well, if you just want to kind of visualize it like that, you got 3 gas molecules flying around, right? And then you get down to only 2 gas molecules flying around. So less gas molecules flying around means less disorder, more order, and more order, less disorder means we would predict that this should result in a negative delta S value. Question on that. So that's a very good thing to keep in mind in a situation like this where you're trying to figure out in this particular reaction, basically, are you increasing the disorder or decreasing the disorder? You could actually make a pretty safe assumption, not necessarily what the numerical value of your answer should be, but you can make an assumption on, and a pretty good one, as to whether your calculated value should be negative or positive based on what's going on in the reaction. So in this case, because we have less gas molecules, we're creating more order. There's just less things flying around, if you want to think about it that way. Because there's less things flying around, there's more order. And we would make a very good prediction here, as we see with the calculation, that we should actually end up with a negative value. Question on that? Okay. And those type of sort of questions, or those type of things that you should be thinking about, are very common type questions that you come across in the thermodynamics chapter. In a thermodynamics chapter, it is very, very common for them to ask you a question and go, not give you any numbers, and just go, hey, just looking at this thing, do you predict it to be maybe spontaneous, non-spontaneous, in order increasing, disorder increasing? So there's a lot of questions that will be in this chapter where they actually will not necessarily give you any type of values or anything like this, but they'll sometimes even say things like, hey, this thing is like delta H is negative and this S is positive. Would you expect it at this temperature to be spontaneous or not? And we'll go through some of those type of questions in this chapter. But it's a very sort of common thing in a thermodynamics chapter to have questions like that, where you sort of have to make this prediction based on these sort of circumstances rather than numbers and calculations. So keep that in mind as we kind of go through this chapter. So as I touched upon in that last example, when we have gases that are being produced or consumed, it can really help us before we even do a calculation make that assumption of, should it be positive or negative, that delta S. And as we see, if a reaction produces more gas molecules than it started, which would be the opposite of what we just had. So if we started with, say, 2 gas molecules, ended with 4, we got to now have 4 things flying around rather than 2. A lot more disorder is going to happen. And that would mean that our delta S would be a positive number, as opposed to what we saw in the actual problem there, that we actually ended up with less gas molecules. So we started with a lot more things flying around, then it kind of slowed down to just less things flying around, and we had a decrease in the entropy and a more negative value. If there's no kind of change in the gas molecules, then you're kind of at that middle of the road. It may be positive, may be negative, but it'll be a relatively small number, as we haven't really increased a lot of disorder or decreased a lot of disorder in that case. So take a second here for the bottom reaction. Based on just the reaction alone, would you predict this entropy change to be positive or negative for this reaction? Particular case here, if we look at the reaction, we have, this is a solid, so we want to look at that. But we do have 1 gas molecule there on the left-hand side. We've got no gas molecules on the right-hand side. That is a solid, not a G. That means we're going from 1 gas molecule flying around to nobody flying around in front of your face, if you want to think about it that way. So that definitely would decrease the order. And because of that, increase the order and decrease the disorder there. And that we would expect the delta S in this case to be less than 0 or negative because of that. Any questions on that? Okay. So let's talk a little bit about the energy change or the delta S of the surroundings now. So to calculate the delta S of the reaction or the system, that is our products minus our reactants. To calculate the surroundings, it's a little bit different. So let's talk about what happens in a normal situation here. On the left, we have the system, which is our flask, is giving off heat and energy to the surroundings. And if you think about it, if the reaction is giving off that energy to the surroundings are going to pick up all that heat and energy, and everybody in the surroundings is going to start kind of flying around faster, right? They got a lot more energy, a lot more ways to kind of move around a lot faster. And we would expect the delta S in the surroundings to actually become more positive because we are increasing the entropy of the surroundings, again, by picking up all that heat that basically is coming from the system. Now, in the opposite here, the surroundings is supplying the heat to the system. And in this case, that's an endothermic process. So what does that mean for the surroundings? Well, it means that as the heat and energy leaves the surroundings and moves towards the system, everybody in the surroundings is going to kind of slow down a little bit, right? Because they have less energy. And if they slow down, we're now increasing the order of the surroundings. We don't have as much crazy movement happening. They've lost energy. They're kind of slowing down. And in an endothermic process, we would expect the surroundings delta S to be negative, or more increasing the order. So there is sort of a relationship between the delta S of the surroundings and the enthalpy value of the system. And that means that the delta S of the surroundings is proportional to minus the delta H of the system. So what does that mean? Well, let's think about what that means. If we have our delta H value for the system here, or the reaction, and if it is positive, that means it's endothermic. And if it's negative, that means it's exothermic. Now, our delta S of the surroundings is proportional to negative delta H. So what does that mean? Well, it means if I have an endothermic process, my surroundings would be negative of the delta H. A negative and a positive value gives you a negative value for the delta S of the surroundings, like in this situation. If my reaction is exothermic, my delta S of the surroundings is negative the delta H, a negative, and my delta H would be negative. That turns that into a positive number for our surroundings here in this situation. So there's sort of that opposite relationship, if you will, of the sign for delta H for the surroundings. And again, it's either the surrounding is going to gain a lot of energy or kind of lose a lot of energy. Questions on that relationship there? Now, does it make a difference, the temperature of the surroundings to begin with? Does the initial temperature of the surroundings sort of make a difference in terms of the entropy change that you would see? And the answer is yes. Right. So if the temperature of the surroundings is like really high to begin with, the amount of heat and energy coming off in, say, the exothermic process from the system to the surroundings is probably not going to make a tremendous difference in the entropy value to begin with, because it was so high to begin with, the temperature, the very high entropy, that added energy coming in from the system is probably not going to make as much of a difference. So for example, if you lit a match and you put your hand near it, don't do this at home or anything like that. Be careful, don't burn yourself. I think that's all the warnings there. If you put your hand near the match, right, you will feel heat and energy sort of coming off. It gets hot, right? Now, if you lit that same match, and again, do not do this at home or ever, and you had your oven on to like 500, you had a very hot oven, 600 degrees, whatever it may be, and you had that one little match, you know, from the matchbook burning inside that oven, you probably couldn't tell the difference between the heat from the oven and the heat coming off of that match. Again, do not try that at home. And, you know, it would make obviously not as much of an impact as if you were kind of room temperature and kind of put your hand near it, you can feel it, right? As soon as you would put your hand in the oven, again, don't do that without proper protection. It will obviously not, you would obviously feel the heat. So the actual initial temperature of the surroundings does make a big difference in terms of sort of the change in entropy that you would obviously witness. Same thing, obviously, if it was very high in temperature in the surroundings and lost a little bit of energy to the system, it may not make a tremendous difference. But under normal sort of temperature values and things of that nature, you know, this is the general trend that we see. As the system loses that energy in an exothermic reaction, we would expect the surroundings to pick up that energy and increase in entropy, and vice versa in an endothermic process. We would expect the surroundings to lose that energy and thus kind of slow down, become more ordered, and we would expect a decrease in the entropy value. Any questions on that there? And this is sort of what, whoa, come back. This is sort of what I was touching upon. And this equation is kind of all over the place here. So let me fix that up for you. Just kind of cross it out, I'll rewrite up here. But to calculate the actual delta S of the surroundings, it is minus the delta H of the system divided by the temperature, and the temperature should be in Kelvin. Yeah. And that's that negative relationship that we were just talking about, that the surroundings is minus the delta H value. And that negative is important because we will see an equation later on in this chapter, which will essentially look almost identical to this equation, except that there's no negative. So keep that in mind as well. We'll actually see another sort of rearrangement of a formula that pretty much ends up dead identical to this one, except for the negative sign. So this is how we calculate the delta S of the surroundings, along with our delta S of our reaction, our system, which was our products minus our reactants. And putting those together, we now know how we can get to the delta S of the universe by basically adding those guys together. Again, this would be like the system. As I mentioned before, the change in entropy of the heat absorbed, it does depend on that temperature like we talked about. And again, if that initial temperature is pretty big, we won't see as big of an effect in terms of it kind of going in and out of the system. And if the temperature is really low in the surroundings, we would see maybe a larger entropy effect. Any questions on those two? Okay. So why don't you give this example a go? We want to calculate the delta S of the system, the delta S of the surroundings for this reaction. And we also want to know, is this reaction going to be spontaneous at 25 degrees Celsius? The delta S values from the table are found on the bottom of the screen. And there's the reaction. So take a few minutes here, calculate both of those things. You might want to calculate the universe as well to help you determine, you know, if you are going to have a spontaneous reaction or not. So take a few. In order to use delta S to sort of do that, you really have to calculate, again, what's known as delta S of the universe. And again, that would be our delta S of our system plus the delta S of our surroundings, basically. And we just learned how to calculate both of those. And in this case, you have enough information to do both of those calculations. We have, obviously, from our table on the bottom there, a way to calculate the delta S of the reaction. And obviously from the delta H value and the temperature value here, a way to calculate our surroundings. So let us start with the system here, or the reaction. And again, if those values obviously were not provided for you, you would go to, excuse me, you would go to the table and look those values up. So what we have is, I believe, on the product side, 2 times the NH3 value, which is 193. So we're going to go with 2 times 193. And that takes care of our product side. We're then going to subtract it from our reactant side, where we have N2, which is 192. So that would be basically 1 times 192 joules per Kelvin per mole. We then want to add it to our other reactant, which in this case is H2, and there's 3 of them. So 3 times 131 looks like. And if we kind of do all that there, let's see, we get 2 times 193 minus 192 plus 3 times 131. Grand total is going to be, if I punch it in again correctly here, try that again. Looks like minus 199 joules. In this case. And does this part make sense in terms of our reaction? So we can take a look at our reaction just to make sure it does make sense. Here we have 4 gas molecules ending up with 2 gas molecules. So again, a decrease in the disorder, an increase in the order. And again, up front, we could have predicted that the reaction was going to be negative because of that. And obviously, that is sort of what we got in terms of the number. Any questions on that calculation there? Now, we can now go to our surroundings, and remember that the delta S of the surroundings is that negative delta H over T, which is temperature. Get that T there. And in terms of the delta H of the reaction, that was minus 92.6 kilojoules. And was the question at the beginning there, I personally am going to convert it into joules because I know I'm going to use it with this number up here, which is already in joules. So I'm going to convert it by timesing it by 1,000, and that will convert it to joules just up front. And again, I'm doing that because I know later on I'm going to kind of use it with this number that's in joules and probably will work out better for us. And usually, again, delta S values are given in joules. If you didn't do that and you left it in kilojoules, it's technically not wrong or anything like that, unless, the question asked you to specifically give it in joules. But usually it is given in joules, delta S values. But again, if you left it in kilojoules, it technically is okay for this question. You'll just have to make sure you convert something at the next step. At this point, we want the temperature again in Kelvin. So that's 25 plus a 273, right? Going to give us 298 Kelvin. And that will end up with 92.6 times 1,000 divided by 298. Get to something like 311. And in my case, I rounded it to joules. And we were okay in that situation because of it. Does this make sense? Well, let's think about what's going on in this reaction. Well, it is definitely a exothermic reaction. This temperature is pretty much a normal temperature, which means that we would expect in this situation the system here to be giving off that energy to the surroundings. And because the temperature here is kind of like a normal temperature, we would expect the surroundings to pick up that energy and kind of go crazy, if you want to think about it that way. And the result of that is we would expect the surroundings to end up with a positive number like we did here as well. So again, if you sort of understand what's going on, you could kind of make sure that your numbers are okay in that sense of positive or negative. Any questions on sort of that logic there? Now, up until this point, for the most part, this number here told us that in terms of the reaction itself, we're sort of decreasing the disorder. This number here tells us that, the surroundings is increasing in disorder because of that exothermic reaction. And it was not really until this point where we have both of those numbers that we could actually make a sort of judgment on, is this reaction going to be spontaneous or not? And again, to do that, that's where we bring in our universe sort of calculation. And again, that is the delta S of the system plus the delta S of the surroundings. And if we put that in there, our system was 199, our surroundings was 311, and that is going to give us a delta S of the universe for this particular reaction of 112 joules here. It's at this point that we calculated delta S of the universe, and it is greater than 0, or a positive number. And that positive number would tell us that this reaction would be spontaneous and it would proceed to the products. So again, it is this actual calculation here in terms of entropy that allows us to truly make that determination of, is this reaction going to be spontaneous or not? Any questions on any of those sort of steps along the way? Now, this reaction is spontaneous. And again, also a reminder that it doesn't mean that this reaction will occur really fast. In fact, this reaction occurs really slow if you don't use a catalyst, which is like the Haber process. Without that catalyst, this reaction takes a very long time to sort of do. It's not very efficient, but in the presence of a catalyst, you can speed it up and it will occur a lot faster. So also a very good reminder that when we determine that something is spontaneous, it doesn't necessarily mean that is a fast reaction. Again, it could be a really slow reaction. We really have no information until you look at the kinetics of a reaction to determine whether or not it's fast or slow. And again, the idea of spontaneity is just that, basically what we are saying is under these conditions stated sort of in this problem at that temperature, if we threw together some H2 and some N2, we would expect the formation of NH3 to happen. Again, could be really slow without the catalyst, maybe really fast with the catalyst, but it doesn't really matter in terms of thermodynamics. What matters in terms of thermodynamics is we would expect the reaction to actually occur. Any questions on that calculation? Yeah.
Um, so how do we know if we like for these types of equations, do we always look for the universe, calculate the universal?
Yeah, so it would be based on the question. So if the question asked you, like this question sort of did, would this reaction be spontaneous? In terms of delta S, you would need to go all the way through technically to the delta S of the universe calculation to determine, if the reaction is spontaneous. It would also mean that probably in that problem, they would give you something kind of like what was given in this problem. You got your delta H value given to you and those type of thing. Now, if the question was a little bit different, like maybe one we did before, where it just specifically asks you, what is the delta S of the reaction? That really has nothing to do with the universe or anything like that. That is like anything that asks about specifically the delta S or the entropy of the reaction or the system. That is when you would just do really the top part of the calculation here, doing the products minus the reactants. If they specifically ask you in the question, what is just the delta S of the surroundings for this, sort of reaction, then you would do the middle calculation only. But if they mention something about, is this reaction spontaneous and sort of all the information you have is delta S information, then you would probably have to do all three of these calculations really to get to the end point there to figure out if the reaction is spontaneous or not. So it does have to sort of, you don't always have to calculate the delta S of the universe. In a lot of cases, we're really just interested in the reaction. So a lot of times you're just doing the top calculation. Sometimes you're just interested in what's happening with the surroundings, which would be like the middle calculation. But if you kind of want to look at the big picture of the whole reaction altogether, and the question asks you about spontaneity of the whole entire reaction, you pretty much got to do the whole picture here and get to the universe. So not always will you be doing the universe. Probably most cases you'll be doing the top reaction or calculation, but that's sort of how you would know you should do the delta S of the universe or not. And it's really the way the question is asked about, is this entire reaction spontaneous or not? Other questions? Okay. So obviously you do need to be able to determine, obviously the delta S of the reaction, which again is sometimes the system. And, if you are just given a reaction or equation in a problem and nothing else and asked what is the delta S of the system or reaction, that's a very good sign. Like I said before, you should go to the table in the back of the book or wherever the table may be, and you do your products minus reactants. In obviously the surroundings, you would be given some type of delta H value, or maybe you would have to calculate the delta H value in a more complicated problem, but you would obviously need that delta H value. And then obviously the universe, you need both of them together. All right, so obviously you need to be able to do that. That is entropy. The third law of thermodynamics is sort of a perfect crystal. Sorry, perfect crystal of a substance has basically an entropy value of 0, and that sort of relates us back to the Boltzmann equation that we talked about earlier. Clearly, if you're going to make a perfect crystal, there's only really one way to do that. And again, the natural log of 1 is 0, gets you an entropy value of 0. It's kind of like a heating cooling curve in terms of our entropy values as we go through it. And again, the entropy down here is going to be less than the entropy value down here is going to start to increase. And then it's obviously going to increase as well. These are the transitions. It's sort of upside down in a normal heating cooling curve, but temperature is actually here, for example. And that would be, for example, if this was ice, that would be 0 degrees Celsius. I know it says Kelvin on the scale. And down here, if this was, say, liquid water, that would be like 100 degrees Celsius, if that was sort of in the Celsius scale. And those are our transitions, right? And as we'll talk about as well, there is sort of a entropy change that occurs at those transitions. And as you may be familiar with, and I'm going to draw it the way we normally look at it, like this. And again, if that's temperature, you know, coming across at like 100 degrees and 0 degrees. This is, say, solid to liquid to gas. And if you remember, transitions occur exactly at that plateaued point. Badly drawn there. We'll kind of straighten out. And that just transition between solid and liquid, that's where melting and freezing occurs. And it does occur at the same temperature. It just depends on what you're doing in terms of the energy. And you might remember that there's a certain amount of heat required to do that. That's the delta H of fusion, right? That's the heat of fusion. So for example, for water, that is something like 333 joules per gram. And that energy, or the heat of fusion, is the amount of energy required not to change the temperature, if you remember, but simply to take something at, say, water, for example, at 0 degrees Celsius, ice, and transform it to liquid water at 0 degrees Celsius, not changing the temperature or anything like that. You might remember that when we go temperature change and the phase stays the same, that's where we use something like specific heat, right, to do that, that Q equals ms delta T. We also have a similar transition that occurs here, right, between our liquid and our gas, and that is where we see our delta H of vaporization, right? And for water, right, obviously it differs with different substances. That's something like 2260 joules per gram to sort of do that as well, that transition. Positive going in one way, negative going in the other way. And again, what we're talking about is right at 100 degrees for water, for example, at liquid water, to take it to 100 degrees, basically steam. And remember that right at those transition points, that's again where evaporation and condensation occurs. At that transition point, you have both phases basically in equilibrium with each other. Not until you get a little bit above the 100 degrees, you got sort of gas, not until below 100 that you got liquid water that's occurring. And as we will see, there is entropy values that are sort of related to that as well. We will see the delta S of vaporization, and that's the entropy change basically that's occurring at this transition site. And we also have something like the delta S of fusion, which also is the, you know, entropy change that occurs with that. And they do follow. So, you know, it is going in this direction. Delta H is positive, right? Endothermic, putting heat and energy in. And as we go from liquid to gas, we would expect the delta S of vaporization to also be positive in that sense, right? Because we're increasing the disorder, and going the opposite way, they both would be kind of negative in that sense. So we'll talk a little bit more about that. But again, as we talked about earlier, we do see that increase in entropy as we go from, say, solid to liquid to gas, because we're creating a lot more disorder, and vice versa, heading back down the other way. We're seeing a decrease in that disorder. And again, our delta S would become more negative as we go in that direction. Any questions on entropy there? So now that we branched out into a new letter of the alphabet like S, let us continue with the alphabet here and talk about another sort of thermodynamic property, which is important. And this is our good friend G. So we get to the letter G here. That's good. G is Gibbs free energy, and it's pretty much what it sounds like. It's free energy available to do some type of work on a process. So earlier we saw that if we look at delta S, for a spontaneous process to occur, we do need the universe to be greater than 0. If it's equilibrium, then it's at 0. So this is one way that you could calculate the delta G of a reaction. The delta G is equal to the delta H minus T delta S. Come here. And these are some of our normal players here involved that we've seen before, and a couple of things that we should be careful of. First off, this is our free energy, or Gibbs free energy. This is our delta H value, which is our enthalpy value. This is our temperature that needs to be in Kelvin. And obviously, this is our change in entropy. So this way of calculating the delta G it is really important to watch your units. So as I mentioned before, a number of times, delta H values are typically in kilojoules. Delta S values, as we just saw, are typically in joules. So very common mistake people make is to not convert the units. You basically got to convert either the joules to kilojoules or the kilojoules to joules, but you got to do some type of conversion. Usually, strict speaking, delta G is given in kilojoules, so usually that is what it's given in as sort of an end result of the number. But again, you do have this sort of unit situation that develops here that you want to be careful of, especially when you're doing calculations. Nice thing about sort of Gibbs free energy is, since it's the energy available to do some type of work, we can oftentimes use its value kind of directly to figure out whether or not a reaction is going to be spontaneous. We'll also see about 3 different ways to calculate delta G. Again, this is one way to calculate delta G. And because we'll see maybe 3 different ways to calculate delta G, it's a good idea just to keep it simple in the sense of I should probably calculate delta G based on the information given to me. So in this type of problem, if you were given a delta H value and a delta S value, this is probably the way you should calculate the delta G, based on what was given to you. If you weren't given those information, we'll see a couple other ways that you could calculate it, but you want to kind of think about what's given to you as to maybe what formula you should use to calculate it. But the delta G value itself will tell us whether or not a reaction is spontaneous or not. If the delta G is less than 0, which means it is negative, the reaction will be spontaneous in the forward direction. So the way the reaction is written, we would expect the reaction to head towards the product side if the delta G is negative. If the delta G is positive, the opposite is true. The reaction is non-spontaneous the way it's written, and we would expect the reaction not to occur the way it's written. But if you happen to reverse the reaction, it would go in that direction. But the way it's written, it would be non-spontaneous. And if delta G is equal to 0, it would be considered a reaction that has basically reached equilibrium. So this is one way that you could calculate the delta G. Again, we would do this if we were given, perhaps in the problem, the delta H and delta S value. Another sort of common way that we could calculate delta G is kind of like how we calculate delta H. Also, the way that we calculate delta S is to basically go to a table and do our products minus reactants. So products minus reactants. And again, we would do the same thing that we did before. The coefficient would need to come into account, and we would go to a table. Just like delta H, we could go to a table and look up what is referred to as the standard free spit that out. It's the standard free energy of formation, delta GF. These are basically table values, kind of like the delta S values you would look up, the delta H values you would look up. You would look up these values in a table. And again, just like we did, multiply the coefficients times those values of all the products added together minus all the reactants added together. Just like delta H, the values that you find in the table will probably be in kilojoules. And just like delta H, things in their standard state will also have values of 0. And again, on the table here on the right, it indicates when we're talking about sort of standard states, what we mean. Again, things are 1 atmosphere in terms of pressure. If we're dealing with concentration, is 1 molar. And temperature is typically 25 degrees Celsius. Any questions on that there? All right, we will stop here for lecture. And it's a good place to actually stop.